Today we are going to actually prove this main equation, that is E equal to k under root s. ये कहाँ से आई, क्या है, and how this equation is going to be used. So I am having this equation over here. Okay, now before I move on forward, there are two things. Whenever you have a E equation, so E is equal to 4.44 f into phi m into n. Now, whenever you have this E equal to this form over here, and this E is actually the voltage over there, and whenever you are interested in S over there for any transformer, this means certainly that you have V cross I, and since you will be working with kVA, so you have this 10 raised to power minus 3 kVA, and if you put this formula in this equation, so this is equal to 4.44 f phi m into Ni into 10 raised to power minus 3 kVA. Now, the reason of actually writing down this equation is very important. If you see this equation, whenever you are designing a transformer, F will be provided by the manufacturer. 4.44 is a constant, it's not changing. Frequency F, if you are certainly working in one region, so it's also constant. But the next two variables, which are phi m and Ni, these are very, very important constants, and listen to this very carefully. Now, when I'm using the word phi m, this actually means that what is the flux inside the core over there. Higher flux means that you are going to have higher core losses. High phi m means high core losses. And higher value of Ni, which is actually, if you remember from your machine's code, the units were ampere turns. So higher value of ampere turns means that you are having more copper loss, because more turns means current you can't control it, because current is dependent upon what? It's dependent upon S. But when you are talking about phi m, we call this factor as the magnetic loading of a transformer. And when you are talking about Ni, we call this one as the electric loading of your transformer. Now these two are very, very important terms. How? Magnetic loading, since I just told you, magnetic loading increases the flux inside the core. Flux increases what? Core losses. And Ni, it actually increases the copper losses. So what happens, what value of Ni you choose or what value of phi m you choose, that are going to decide your transformer losses overall. So whenever you are designing a transformer, the term of this magnetic loading divided by this electrical loading, we are going to call this one as phi m divided by Ni, and we are going to keep it constant, not for all the transformers, only for that particular transformer. अगर हम एक 100 kVA का ट्रांसफार्मर डिजाइन कर रहे हैं, so हम वैल्यू ऑफ R, ठीक है, ये R है, डोंट कंफ्यूज दिस वन विद गैमा, बिकॉज मेरा R थोड़ा सा गैमा जैसा है. नाउ बेस्ड ऑन दिस R, इफ वैल्यू ऑफ R इज लार्ज, इसका मतलब क्या है? माय ट्रांसफार्मर डिजाइन इज गोइंग टू हैव मोर कोर लॉसेज एज कंपेयर्ड टू कॉपर लॉसेज. अगर मेरी R की वैल्यू कम है, तो इसका मतलब है कि आई एम हैविंग अ डिजाइन विच इज मोर इंक्लाइंड टुवर्ड्स लेस iron losses than copper losses over there. So it's actually based on the designer that what value you want to use. Now, अगर मेरे पास phi m बड़ा है, तो वो क्यों ऐसा? इसकी रीजन सुन लो एक बार. Reason for phi m being large, we know what is phi m. Phi m is equal to B dot A. Bm कहाँ से आना है आपके पास? Bm is the flux density of your, this is actually flux density, don't call it flux. This is the flux density at which your material is going to saturate. So अगर आपने एक अच्छा मटेरियल उठाया है, उसकी flux density Bm, maximum flux density, it saturates supposedly at 1.7. So at 1.7, when you plug in this value, you are going to get AC. अगर आपने phi m की वैल्यू ज्यादा रखी होगी, तो आपके पास एरिया ज्यादा है. Bm तो मटेरियल की वजह से डिसाइडेड है. अगर आपने phi m की वैल्यू कम रखी होगी, Bm स्टिल वही 1.7 या 1.5 डिपेंडिंग अपॉन द मटेरियल है, A की वैल्यू कम आएगी. Now, area is the area of that central core on which the windings are going to be done. मेरे पास area ज़्यादा आता है, core losses ज़्यादा आएंगे. But this is very important factor. If area is going to be large, the length of the winding is also going to be large. So copper losses are also going to increase. They are interlinked. You can't say this thing that एक को कम करेंगे तो अगला वाला बढ़ जाएगा. So this is interlinked over there. So the value of R, that is pi m magnetic loading divided by the electric loading Ni, this factor you have to choose what factor you want to use over there. Now we know that E is equal to, oh sorry, not E actually, I'm going to use with the book one. This is 4.44 into F into phi m into N into I into 10 raised to power minus 3. This is the same formula from the above. Now I want to include this R inside this equation. What is R? R is equal to phi m divided by Ni, and I want to include this one in this relation. So what will happen? This will be equal to 4.44 into F into phi m square divided by R into 10 raised to power minus 3. Agreed? Same thing. R include kar diya maine, and I have now phi m. Now this phi m, from here I can deduce what is phi m. Phi m is equal to R into S into 10 raised to power 3 divided by 4.44 F, and I have this. Now what is inside this one R, what is actually the constant which I am going to assume. F is the rated of the kVA, and then this is a constant 10 raised to power 3. Frequency is also constant, 4.44 is a numerical constant. Now you have this phi m. Now coming back to the same equation, that was ET equal to 4.44 F into phi m. ET क्या था? Volts per turn. अगर यहाँ पे E होता सिंपल तो it was 4.44 F phi into N. It's not N, it is just ET, so there is no N. So if I just put this phi m in this equation, I will have ET equal to 4.44 F into, and this whole term, this is R cross S into 10 raised to power 3 divided by 4.44 F. Now you can see this is without the under root, or this is with the square under root. So what happens? This ET is equal to, in the under root we have 4.44 FR into 10 raised to power 3, and I can separate under root S. Now if you see this value, what is 4.44? Numerical constant F. If you are in one region designing for a similar kind of transformer, frequency is same. R, again a constant assumed by the manufacturer or designer actually, and 10 raised to power. So I can call this ET equal to K, which is a constant, under root S. So what you are going to assume, you have to design a transformer, you will assume the value of K. The value of K has to be assumed by you. Why? Because आपको नहीं पता कि आपने phi m को बड़ा रखना है या Ni को बड़ा रखना है. So what you are going to do, you are going to assume a value of K. Certainly there is some range. Now what is that value of range? Supposingly you have a single phase core type transformer. If you have a single phase core type transformer, then this value of K is from 0.75 to 0.85. And if you have a single phase shell type transformer, this value of K is from 1 to 1.2. कोई मुझे बताएगा यहाँ पे कि फर्क क्यों है इन दोनों में? सिंगल फेज है दोनों, लेकिन दोनों की K की रेंज में फर्क क्यों है? कोर के लिए और शेल के लिए. Answer is in the first lecture we did for this course, first or second lecture. Shell type transformer, they have a better flux linkage, they have less core losses over there. So you can have better magnetic loading over there. Better magnetic loading means better R. Better R means higher value of K. So that's why the K value is better. If you have a 3-phase core type transformer. Now, in core type, you have two designs. One is a distribution transformer, other one is a power transformer. And what was the main difference in these then? Distribution transformer is working for 24 hours a day, 365 days a year. So here you need to keep the core losses small. So the value of K which you are going to use is approximately 0.4 to 0.7. And when you are designing a power transformer, then this is going to be approximately 0.6 to 0.7. These are range. ये मैं सिर्फ range दे रहा हूँ, ठीक है? It's totally your assumption or your design related. You can use 0.4. अगर आप 0.4 इस्तेमाल करोगे for a distribution transformer, इसका मतलब ये है कि आप जब डिजाइन के एंड पे पहुंचोगे, आपका ट्रांसफार्मर में कोर लॉसेस कम होंगे, कॉपर लॉसेस ज्यादा होंगे. अब ये आपके डिजाइन पे डिपेंडेंट है कि दे वायलेट द लिमिट्स ऑन विच यू आर वर्किंग. हो सकता है बाबा ने आपको कहा जी कि आपने एक ऐसा ट्रांसफार्मर बनाना है जिसके अंदर आपकी कोर लॉसेस जो हैं 500 वॉट्स हो और कॉपर लॉसेस जो हैं वो 3 किलो वॉट्स. लेकिन आपने के की वैल्यू जो अज्यूम की, उसके बाद जो एंड में आपके पास ट्रांसफार्मर बना उसमें कोर लॉसेस तो बिल्कुल ठीक है, लेकिन कॉपर लॉसेस 3 किलो वॉट से ज्यादा आ गए. देन यू विल गो बैक, change the different value of K and then redesign it. Okay? So this is 3-phase core. And if you have a 3-phase shell type, then and 3-phase shell type are normally used only for power transformers, and they have a better one. Their range is from 1.2 to 1.3. They have a very higher range because 3-phase shell, but again they have a problem of heating. They have a problem of cooling themselves, so they are only run for like 7-8 hours or maximum 12 hours, and then they have to be cooled down. Plus they have to have some forced cooling mechanism so that you can decide. In this course over here, we are more concerned with this design of the distribution transformer. We will also touch this power transformer, but our main aim is the distribution transformer, that is 3-phase core type, and this is the same transformer that is outside your houses or industrial areas where you are converting 11 kV to 400 volts over there. Now, one thing very important which must have been told to you in your machines course also, that whenever a transformer is written on the nameplate rating, they will write it as 11 kV / 400 volts. Now, these are line to line voltages. If you do the mistake of taking them as phase voltages, you have destroyed your design from the very first phase, because all the windings are phase wise design. So when you want to find out, supposingly you want to find out V1, what is V1? I told you V1 was the high voltage winding, and since this is phase voltage, you will have to, now this is totally dependent upon on 11 kV side you have delta, and on the other side you have Y. Now when you have 11 kV in delta, the phase voltage and they are same. So this means that the, a second, let me just so V1 phase is the same as V1 line to line, and that is 11 kV in this case. Now this is the normal standard in Pakistan, that 11 kV side, that is delta connected, and the 400 volt side is Y connected. But this can be opposite in your design or any exam paper. So don't take it something कि जी normally हमेशा ऐसे ही है. It can be different as well. It can be YY, it can be delta delta. Certainly there are some problems of using them in YY or Y delta or something different. Now when we are talking about the second side, V2, remember I told you one subscript is for the high voltage side and second subscript is for the low voltage side. There is no concept of primary and secondary winding. We only use the word low voltage and high voltage winding. So when I have V2 phase, I want to find out V2 phase. This will be equal to 400 volts divided by under root 3. G, please calculators out. And if I do any mathematical mistake during all this whole semester, please point out. ये नहीं है कि सर गलती कर रहे हैं, जाने दो. At the end of the semester पता चले कि हमने ट्रांसफार्मर ही गलत डिजाइन किया. 230.94 volts. So this is my phase voltage for V2. Now, supposedly I am not starting a design, but since I have just proven over here that ET is equal to K under root S. So I have to choose some value of K, and I told you that when you are having a three-phase, this is actually a three-phase 100 kVA transformer of 11 kV slash 400 volt. 100 kVA, I guess ये हमारे department के बाहर I guess 400 kVA. 100 kVA is a little smaller one, so 400 kVA. But I'm going with the 100 kVA design. This is also a distribution transformer. Now, when I have a 100 kVA transformer, I know the ranges for a three-phase core type is from 0.4 to 0.7. Now 0.4 to 0.7, G, what should I use K? क्या use करूँ? 0.5, चलो 0.5. So if I use 0.5, this is again your total discretion. You have gone with the 0.5, and here in this one you have like 100 kVA. Don't use K over there. Already it is 10 raised to power 3 in the formula, so you don't need to write down that K factor. So this comes out 5. It comes out 5 volts per turn. Now, remember, when you have 5 volts per turn, this is actually telling you that this is the voltage per each turn. Either you are on the low voltage side, either you are on the high voltage side. Now, since I am not concerned with the high voltage side at present, why? First of all, I have to design the core. On that core, I have to put the low voltage winding. Then there will be some insulation. Sorry. Let me turn off my mic. Okay, so when you have a 5 volts per turn, this 5 volts per turn is telling you that your volts per turn is going to be the voltage per each turn. So when you are talking about the low voltage winding, so if you have a low voltage winding over here, and in this low voltage winding, I am concerned with what is N2. I will find out. I know your ET is going to be equal to V2 divided by N2. This is the formula. So based on this formula, can I find out N2? N2 will be equal to V2 divided by ET. So VT is 230.94 divided by 5. The क्या है value? Exact 46. Get a point, please. This is a design course. Please up till at least 2 or 3 significant digits. Do not miss. 46.188 turns. Now, this is turns. You cannot have a fraction number of turns. Now, one thing very important. Many of you will be designing your FIPs, having some power electronics transformers inside it, and talking about some high frequency chopper circuits from your power electronics course, or if you are doing an FIP based on that. Those are high frequency transformers. There the frequency is something 10 kilohertz, 40 or maybe even 100 kilohertz over there. In those transformers, it is practically possible to make a fraction of a turn. Maybe 0.2 turns, 0.4 turns, 0.5 turns. That is possible. Based on what? If supposedly you have a core over there, I am talking about a high frequency transformer. Your turn starts from here. You do it 1 turn. You want to do 1.5 turn, you will go up till this point and take the wire out. But when you are designing a high frequency transformer and it's a high power transformer, something 100 kVA, the core size is this. When you are going to have a low voltage winding, it will be something like this, and then there will be some air gap and then a high voltage. Now the size is very huge. You cannot have point turns over there. Why? Because when you have an 11 kV wire coming in, that 11 kV wire has going to be moving like supposedly for like 40 turns, whatever the value, supposedly 46 turns for 400 volts. Now when you want to do 0.118 turns, this means the point of entry and the point of exit, they has to be same. Otherwise the wire will be moving in the oil. So in low frequency transformers, the normal advantage is this, that you will make it 47 turns over here. You will not reduce it. Okay? You will have a ceiling approximation, which means if this is 46.188, you will make it 47 turns. Now, why you are not making it 46? Because if I make it 46, what happens? The actual DET, that is 5 volts per turn, इससे बढ़ जाएगा. इसका मतलब यह है कि मैं जो K वैल्यू मैंने अज्यूम की थी 0.5, वो उससे भी कम हो जाएगी. So I am going with 46.188 changed to 47 turns. So this means I have 47 turns on the low voltage side, and based on the same calculation, since you know this is now 47 turns, now based on this 47 turns, can you find out ET that is actual? क्योंकि आपने number of turns को approximate किया है, so you have to find out ET actual, and that ET actual will be equal to 230.94 divided by 47 G. 4 point, exact 4.9. Points के बाद, please, this is a design course, don't miss that points afterwards. 4.913. So this is volts per turn. Now this is the ET actual you are again going to use for high voltage winding, that is the, so what is going to be N1? N1 is equal to 11 kV divided by 4.913 volts G. Give me a value. Divided 11 kV, 11,000 divided by 4.913. 2 point कैसे हो गया यार? 2238.957. अच्छा, now here you have 957. So even if you just make it an approximation of 2239 turns, this will not create that much problem. Now changing this 0.957 to full form, you don't need to actually now do this ET actual. That ET actual will almost be the same. The only difference will be just in point. Okay? Because you have to design it from the low voltage side, because low voltage side has less number of turns. वहाँ पे अगर आप थोड़ी सी भी fluctuation करते हो, it will have more problem. So on the high voltage side, even a turn of 1 turn or 2 turns difference is not going to make that difference. Now when you have designed N1 and N2, after this one, what is ET formula? ET is equal to 4.44 F into BM into AC into, sorry, this is N over there, okay. This is not going to be there. Okay, based on this one, इस फॉर्मूले में मेरे पास क्या है क्या नहीं है? ET मौजूद है? फ्रीक्वेंसी पता है? BM पता है? BM is based on the material you are going to choose. Now, if you are a good manufacturer and you don't want to earn some bad reputation, whenever you are going to use a material, if that BH curve saturates at that point, you are going to use this value. But if you are a very bad manufacturer and you want to earn some fast money, you will use something, a value of B over here. The disadvantage would be your transformer will be very good and it will be saleable because you have used less iron, you will have less core losses, very good. But the problem would be that the current it would be taking at no load will be high frequency third harmonic current. The current waveform is not going to be sinusoidal. Why? Because this is H, this is B. So up till this point this is linear, but afterwards when it goes up till this point, the current waveform does not remain sinusoidal. It actually becomes, let me draw it again, I drew it in the first, it will be something like this. This is a third harmonic current more inside this green color waveform. So transformer chalega, no problem. Now this high frequency currents are going to pose problems inside your transformer, maybe to the other supply which is attached with that transformer. So otherwise it's going to run very fine, and this is the same problem also in this fans or motor design. अगर आपका manufacturer, जो कि normally पाकिस्तान में जितने manufacturer, they always want to earn fast, so they always choose a value of B that is more in the saturation region. More in the saturation means that you are having a huge current spike. यहाँ से लेके from this 0 point up till this point, this is linear, almost linear. But after this point from here to here, this is not linear. For a very large increase in I, you are getting a very small increase in B, this one. So if there is a big bulge, now practically मैंने यहाँ bulge बनाई है, this may not be this much big, but I've just drawn it a little bit big so that it's visible to you. But it is having a high third harmonic component. So now assuming I am something in this value, I have taken this B value. So the BM value, I have taken something CRGO steel. This value comes out to be 1.7 Tesla. Okay. Some manufacturers, they use 2.1, 2.5. Sadly, we don't have that big material over here or better material. If I have something good hands on a very good material, maybe I can then have this BM equal to 2.3 or 2.4 even. So when I have chosen BM, can I find out from this equation what is AC? AC would be equal to ET. Remember, I have to use the actual value of ET, not the first calculated. This is very important. Divided by 4.44 into, this is F into BM. जी, what is ET? जरा मुझे value बता दो. Okay, sorry. ये बढ़ गया. 0.0130. दोबारा कहते 4 point. 0.01. नहीं, ये आप मुझे value ना बताओ, पहले value पुट कर दो मुझे. ET क्या था actual? 4.913 divided by 4.44 into 50 into 1.7. 0.0130. नहीं आगे पूरा बताओ, पूरा ये मैं बताता हूँ. 0.0130 180 repetition of 180. अच्छा, the reason, what are units of this? Area, क्या units of this? Meter square, because I am working in SI units, so this will be meter square. Now meter square is a very big area. I don't want to work in this one. I am going to work in millimeter. Okay, it's a better unit. Now, the reason I have written after this point so many numbers, because when I am going to convert this into millimeter square, I am going to multiply it by 10 raised to power 10 raised to power minus 3 plus 6, because millimeter square. So when you are going to write AC, this is going to be 130123456. So this will be 13018.018 millimeter square. Please have a habit of writing down after the point or decimal at least 2 to 3 decimal. This is very important. और यहाँ पे स्पेशली व्हेन यू आर इन मीटर स्क्वायर, अगर मैंने मिसाल के तौर पर यहाँ 0.013 के बाद छोड़ दिया होता, आई वुड हैव बीन मिसिंग अ वेरी लार्ज चंक. ठीक है, दिस इज वेरी इंपॉर्टेंट. नाउ यू हैव गॉट द एरिया AC. नाउ दिस इज द कोर एरिया और this is the iron area that I require, 13018.018 millimeter square. मुझे इतना आयरन चाहिए जिसके अंदर मेरी फ्लक्स डेंसिटी 1.7 टेस्ला होगी, और इसके ऊपर मैंने वाइंडिंग करनी. नाउ द फर्स्ट केस वेरी इंपॉर्टेंट. आई एम नॉट गोइंग टू मेक अ सर्कुलर और अ 3 स्टेप और अ 2 स्टेप कोर. आई गो विद, मेरे पास आई एम गोइंग टू गो विद अ सिंगल step core. By single step I mean I have something like this, which means this is that single step, and this distance I call it D. What is D? D is the diameter of the circle, and certainly it's also the diagonal of the square. Now the square has 2 dimensions, A and A, the square. Now before I proceed on forward, there is one problem over here. Since you are going to stack lamination, what you are going to do, you are going to have laminations over here, and those laminations are going to be in this way. Now these laminations can have a thickness from 0.8 to 0.9 or 0.95 millimeter or even 1 millimeter, or maybe if you are a bad manufacturer, then you have a little bit more thickness. Smaller the thickness, better the manufacturer or better core losses you have. Now, since the area you have been given or you have calculated is the net iron area, but when you are going to stack laminations together, there is going to be a resin applied in between them. If you are a very good manufacturer, you will spray that silicone resin with some sprayer. Or if you have a very bad laborer or worker having over there, he will use that brush and apply that insulated resin. And if it is very thick, when you are going to stack the laminations together, the area is going to be large. Now, you have found out that your net iron area is 13018.018 millimeter square. Now, before I proceed on, there is a factor which is called as Ks, and we call this one as the stacking factor. A factor which tells you that your area, actual area, is how much less than the given area. So when you are trying to find out Ag, which is the gross area, what is Ag? Ag is the gross area. So what is gross area equal to? Gross area is equal to your net iron area divided by the stacking factor. And what is the stacking factor range? This stacking factor range is from 0.85 to 0.95. I hope you are getting the idea. What does stacking factor mean? If your laborer or your workmanship is good, your stacking factor will be something 0.95. आपका resin भी अच्छा है, पतला है, it's a good insulator also, not that very weak one. So you are going to have 0.95. लेकिन आपने insulator जो बीच में लगाना है, you are going to spray it or maybe you are going to apply with some brush or whatever, that is not a good material, उसकी thickness ज़्यादा है. So when you are going to stack laminations together, that is going to increase the area. अब हमें net iron area, iron का area हमें चाहिए 13018.018 millimeter square. Including that one and including that area of the insulator, you are dividing it Ai divided by Ks. So this will give you the gross area. So now assuming कि मेरे पास stacking factor, I have a very good workmanship and supposingly I go with 0.95. ठीक है, मेरा insulator बहुत अच्छा है, it's being sprayed, it's not being applied with a brush, because when you are applying it with a brush, certainly there will be non-uniformity. But if you are spraying it on the lamination, then certainly you can assume it that it will be something homogeneous. So when you have it, so this will be 13018.018. G, please give me the value, or let me write down the value here. What is Ag? 13018.018 divided by 0.95. 0.95, let me tell you, is a very, very good stacking factor. Otherwise, कोई मुश्किल ही है कोई इतना effective. It can be ranged from 0.85 or 0.9. हाँ, दोबारा बोलो. 103 1370.17. चलो 176 बस बहुत है, इससे आगे क्या. So this is your area. This is the area, actual area जिसका आपने core बनाना. It includes the factor of your stacking of the lamination. This is the gross area. Now, if you see over here, I have chosen a single step core. This is called as a single or one step core. Now I know the area. It has to be a square. So will this AG be equal to pi d square by 4? अगर मैं r के रेज में लिखा तो pi r square होता. Now since I have written in terms of diameter, because I need to find out that d, so this will be pi d square by 4. So if you put in this formula, this d is equal to 4 into Ag divided by pi and under root. G, plug in the value. This is 4 into the value of Ag is 130 7013.17 divided by this is 3.141592654.
132.08.
क्या है जी 132.087 दोबारा बोलो क्या हुआ 137 हाँ सॉरी ये यहाँ पर गलत हुआ है 13703.1 जी इसको जरा ठीक कर दो 132.088 तो काफ़ी है इतना काफ़ी है मिलीमीटर में है मैं So I have my diameter equal to 132. अब यहाँ पे हम approximation कोई नहीं करेंगे, please very important, because this is millimeter and you can cut with an accuracy of something 0.1 or 0.2. ठीक है, that can be done. अब ये 0.88 है, I can call it 0.1 mm. It's totally up to the manufacturer जो वहाँ काट रहा होगा. I will give this design. It's totally up to वो exactly 0.88 तक नहीं काट सकता तो 0.1 जरूर काटेगा. Now when you have got this D, over here. Can I write it as D is equal to or D square is equal to A square plus A square? Pythagoras theorem. Single step 4. ठीक है जी? So from here, can I find out A equal to D square by 2 under root 2? So this is D, what is D over here? 132.088. I am squaring it, divided by 2, just give me the value or give me the value of A. D. 93.400 mm. बस ठीक है 400. Now what is this value? A is equal to 93.40. If I go back on my single stage, this means that this length to this length, this is 93.40. Now, it's not part of this design, it's actually a different design, but let me give you an idea over here. If I have a 93.40 mm, 93.40 mm, how many laminations would be there? You can decide on this one. How? You know the thickness of one lamination, that is 0.85 or 0.95 whatever. Divided this total length A by the thickness of one lamination, you will find out the total number of laminations you have. ठीक है, मैं यहाँ पे ये step नहीं कर रहा हूँ. Reason behind, because a single step core is rarely used. Now if I go towards a two-step core, if I have a two-step core, let me draw that diagram now. If I have a two-step core, in fact let me use the circle form first. And so what is this? This is that second step, and this one is your first step. Please remember, the internal first one is called as the first step, the second step is here also, and it is also here. Now question over here, when you are going to make a two-step core, certainly what is the advantage? कोई बताएगा two-step core over one-step core, what is the advantage? Air gaps are less, the fill area of the circle is more. When you have a two-step core as compared to a one-step core, they have less vacant spaces over here. This one, these areas are air, because when you are going to design a transformer, if supposedly you have a two-step core, उस two-step core के ऊपर आप windings नहीं करना शुरू हो जाएंगे. You will first of all put an asbestos or a cylindrical sheet on it and then do the low voltage winding. Reason, because these are very sharp edges. If you put the binding on it, maybe the abrasive material or the insulation on those copper wires peel off, and afterwards it will have a short circuit. So you will put a little bit 2 or 3 mm thickness asbestos or a cylindrical sheet, and that is going to keep it in circular form. So if you are using a 3-step core, the percentage fill area, let me give you an answer. The percentage, if you are using a 2-step core, the fill area is approximately 64%. So only 36% is air gap. But if you are using a 3-step core, that value goes on to 84%. So normal practical transformers, whenever they are designed with 9 or 10 or 11 step cores. And 9 and 11 step cores, they have a percentage fill area of 98 to 99%. You can't achieve 100% unless and until you increase this number of steps to infinite. And increasing them to infinite means that each and every step you are going to have a different lamination. So the cost is also increased, the labor cost is also increased over there. Now coming back to this 2-step. Now over here, what is this distance from here to here? D is the circle radius. What is this distance from here to here? It's also D, because it's also the diameter of the circle. Now, what is, if I call this distance as A, okay, and I call this distance as B, G. It has to be same. This is also equal to A. Okay? This is also equal to A. ये practically circle नहीं है पूरा ऐसा. It's not up to the scale. Otherwise, if this is A, this has also to be A. So overall, what is this distance equal to? B. Now, based on this one, can you tell me what is the total area formula of this 2, 1? D. You have A, B and all that stuff over here. तो बताएगा एरिया कितना है टोटल? एक सेकंड, मैंने यहाँ पे छोटी सी गलती कर दी है, मुझे लग रहा है. एक सेकंड, जस्ट लेट मी. This is actually A. Sorry. This is and this is B. Okay. G. Now, sorry for that. G. What is the total area of the transformer or the core actually? Come on, you have the dimensions, you have A, you have B over here. Can you write down the formula for this one? देखो जी ये कितना है? What is this distance? B. What is this length? A. So the area is equal to AB. This one plus what is this distance? This is B. What is this distance? This is A. So this is AB plus AB minus B square. Agreed? देखो ना, when you are having AB, what is AB? AB is this one. And what is the next AB? Next AB is going to be this one. So you are including the center area 2 times. So you have to subtract it 1 time. So what is that area? This is this area over here, this one to this one. This is B square. So the total gross area is AB plus AB minus B square. Everyone has got it? Now, let me turn off this one. Wait a second. Let me. Okay, I have this one. This area, the green colored shaded region over here, this one, in the center. इसका area क्या है? AB. What about this area? It's also AB. It's a circle. It's a symmetrical circle. So अगर ये AB है, this is also AB. Now when I am including this AB plus this AB, the center one is coming 2 times. So I have to subtract it. And what is that distance? This is B. This is also B. So B plus B multiplied by B, B square. So that's why this is AB plus AB minus B square. Got it? Now, still this does not solve the problem. How I am going to find out the values of A and B? नहीं, ये तो just variables है. These are just variables. मैंने अभी कोई value नहीं दी उनको. अभी तो value वाला मसला भी पड़ा है. अभी value वाला मसला पड़ा है. मैंने अभी सिर्फ variables define किए हैं. A and B. ठीक है? नहीं. देखो, if this is A, this distance is B. ये distance A है तो ये distance B है. सही है ना? Suppose किया, मैंने suppose किया, अभी मैंने value नहीं बताई है. I have just supposed it over here. Please remember. नहीं. A B की equal बिल्कुल नहीं है. किसने कहा A B की equal है? A and B they are totally different from each other. A certainly बड़ा value है, B छोटी value है. मेरे पास अभी तक कोई फार्मूला नहीं है जिससे मैं A निकाल सकूं, B निकाल सकूं. मैं क्या निकाल सकता हूं अभी तक? सिर्फ I can only find out D from this formula which I have already found out. मेरे पास सिर्फ D है. मेरे पास ना A है ना B है. Now coming to how I will find it out. If I go back on this one, what is this angle equal to? Theta 1. And what is this angle equal to, which is theta 2? In fact ये मैंने diagram काफ़ी गंदी कर दी है. Let me make it a new one ताकि ये समझ आए, because your assignment is actually based on this one. So this dimension is A, this dimension is A, this dimension is B, and this dimension is B. ठीक है जी? ठीक है? It's a circle over there. Now this angle is theta 2. This angle is theta 1. They both have the dimensions D. कोई बताएगा theta 1 और theta 2 की वैल्यूज क्या होगी या कैसे निकालेंगे? एक सेकंड, one at a time. हाँ जी. Okay, let me write it down. Sin theta 2. टेंजेंट लगा लें, चलो. It's totally up to you. Tangent theta 2. G, what it is equal to? Tan theta 2 is equal to B over A. And what is tan theta? So इसीलिए मैंने कहा तुमने tan लगवाया, इसीलिए. You have to use sin over here. G, what is sin theta 1 equal to? जी, sin theta 1. Sin theta 1. A over D. Sine perpendicular over hypotenuse. What is perpendicular? This is this distance, and this is hypotenuse. So this is A over D. What is cos of theta 2? A over D. So this is also A over D. This means they both are same. अब ऐसा कौन सा वैल्यू ऑफ एंगल है जिसका साइन 45? So you are mathematically getting the answer that theta 1 and theta 2, they are going to be 45 degrees. So you are going to get, so now you know that theta 1 and theta 2, they both will be 45. Now when you know your D value, आपको D value पता है from the previous calculation. From here you can easily find out what is A. A is equal to D cos theta 2. What was D? D क्या value थी? 132.088 millimeter multiplied by cos of 45. D value बता दो please on this one. What will be B? You can use B equal to A tan theta 2, is totally up to you. A tan theta 2, this is A into tan of 45. A अभी निकलेगा यहाँ से. हाँ जी, क्या वैल्यू है? 93.400 mm, and multiply this 93.400 multiplied by tan 45. 93.4. अच्छा वो, हाँ वो तो सिंपल, ठीक है. 93.4. So you have your A and B. ये गलत नहीं है था, मैं कुछ B क्यों सेम कैसे आ गया? नहीं tan 45. नहीं एक सेकंड. हमने B, what will be B equal to tan theta 2. How can be A and B same? A and B same नहीं हो सकते. क्या है? ये भी सेम नहीं हो सकते. कि क्या गलती की है बताओ मुझे प्लीज. गलती क्या की है प्लीज? A and B can't be same. They both are different length. गलती क्या की है यार इसके साथ क्या? But it works completely fine in section B. When your lecture comes at the very end, it starts to behave erratic. Anyway, let me solve this. हाँ जी, क्या है मतलब? गलती क्या की है हमने जी? थीटा 1 and थीटा 2. थीटा 1 का एक सेकंड. This one is B, theta 2, this one is A, this one is B. हाँ ये आपको खैर नजर नहीं आ रहा है. हाँ जी, give me the correct answer. हाँ जी, क्या गलती की है हमने? हाँ जी ये गलती है, मुझे पता चल गई है. क्या? हाँ अब बताओ क्या बता रहे हो? जी बड़ी बेसिक सी गलती है, बहुत बेसिक सी. गो बैक ऑन दिस वन. क्या गलती थी यहाँ पे? देखो, आई हैव रिटन साइन थीटा 1, आई हैव रिटन कॉस थीटा 2. ठीक है, दोनों की वैल्यू सेम है. ऐसी कौन सी वैल्यू ऑफ थीटा 1 और थीटा 2 है जिसके ऊपर दे बोथ हैव द सेम आंसर। मैंने उस वक्त जानबूझ के आगे चलने दिया, मैंने कहा देखते हैं कोई मैथमेटिकल बंदा यहाँ पे इसको आंसर करेगा। कम ऑन भाई, टेक्नोमेट्रिक टेबल रटे लगाए हुए होते हैं। साइन थीटा इज इक्वल टू कॉस थीटा, कौन सी वैल्यू ऑफ एंगल है? Sin 30 is equal to cos of 60. Yes. They both have the same value. यही वो चीज है, theta 1 will be 30 degrees, theta 2 will be 60 degrees. ये नजर आ रहा है आपको टेबल इस ग्राफ के अंदर भी कि theta 1 and theta 2 they both are different. How they can be 45? Please use your brains. This is very important. मैं जानबूझ के गलती प्रोसीड फॉरवर्ड की ताकि आप लोग इसको पकड़ो। One angle is 30, other one is 60. Sine of 30 is under root 3, 1 by 2, I guess. Sine of 30 is 1 by 2. Cos of 60 is also 1 by 2. So the value is not 45. This is wrong. Please, this is very important. The values are 30 and 60 degrees, and based on this, now you can find out your whatever calculations. Let me remove this one all. D, what is D? 130.088 into what is cos of, let me find it out. Cos of theta 2 is cos of 30 degrees, and here I have जी क्या है वैल्यू है, A की वैल्यू क्या आ रही है? 114.388 mm. So this is 114.388 into tan of 30 degrees. One 114.388 into tan of 30. G, please answer. 66.04 mm. 114.388 and 66.04 mm. You have there. Now, this was very easy because it was a two-step core, still after doing that blunder also. When you are going to have a three-step core, bolo. Yes, without doing this calculation, even if you just see this overall, you know A and B, they are angles over there, so based on the opposite side angle, you can also evaluate it. They can based on whatever calculation. Now, this is doable for two-step core. But when you are going to do it or do this calculation for a three-step core, so if you are going to have a three-step core, so when you are going to have a so this is your step number 1, this is step number 2, this is step number 3. Now here, it's totally up to you. You want to call this length equal to what? You want to call this length equal to up, and you want to call this length equal. Supposingly I use A1, A2 and A3. I don't use A, B and C. A1, A2 and A3, they are easy for me. Now based on this one, this angle I can call this distance is D, certainly, that will be already known to you, and this angle I can call it theta 3. This angle to this one I can call it theta 2, and this angle to this one I can call it theta 1. Now question is this: is there a relationship between theta 1, theta 2 and theta 3? So relationship has? Practically no. In a circle there is no relationship over here. Now question here is it, how you are going to find out theta 1, theta 2 and theta 3. Now designers of transformers, they don't do this calculation. What they do, they just find out an approximate formula, and that approximate formula is this, that you have your theta angle equal to 90 degrees divided by n plus 1. This gives you that minimum angle of that transformer over here. So when you are going to have supposedly a 3-step core, you will just add 90 divided by 3 plus 1, 4. The answer comes out to be, this is 90 degrees divided by 4. So this comes out to be 22.5 degrees. So this is that angle theta 3, the smallest one which you are going to have. And in the same way you can go on with the second and third step. But this is an approximate. Your assignment is this. You have to find out this theta 1, theta 2 and theta 3 mathematically. Now how you are going to do it? The hint is this. You know this is A1, A2 and A3. You also know these dimensions, this dimension over here or this dimension over here or the other one. They all are symmetrical. So using your trigonometric equations over here, you can again write down your gross area equation using some variables A1, A2, A3 with some angles and make this area equation in terms of one variable and then differentiate it with respect to another variable. You will arrive at the maximum area for AG. And at that maximum area DAG divided by that variable, the slope of that curve is going to be 0. So you will equate it equal to 0 and you will find out that theta 1, theta 2 or theta 3. Okay? So this is for the 3-step core. You have to do this assignment. You have to find out this theta 1, theta 2 and theta 3. Now actual designers, they don't do it, they just go with this approximation formula, that is 90 divided by 4. Now your actual answer, which you will find out by your assignment, you will find out theta 3 is something 21 point something angle. So it's not that much different. So you can't say it's going to be an actual circle, it will be close to a circle with a little bit oval shape on some side. Okay? So but do this assignment, this is your assignment over here. So you have to calculate this theta 1, theta 2, theta 3 for this 3-step core. And for a 3-step core, the fill area, as I told you previously also, is equal to 84%. Now practical transformers, they don't go for 2-step or 3-step cores. They normally go for 9 to 11-step core, and in that cases, the fill area, which means the area covered by that core on that circle, it actually is up till 98 to 99%. That fill area is available over here. The table is also available at page number 217 of this book. Okay. Or maybe you don't even need to memorize this. Whenever question is given, we give you this fill area percentage over there. Okay. So this is your assignment over here. Take 1 week's time for this one. Try to calculate. This is a mathematical assignment. Try to solve it. I've given you the hint. First of all, write down AG in terms of those equations. Make it into one variable, differentiate it, and then you will find out that value of theta 1, theta 2 or theta 3. And certainly theta 1 and theta 2 and theta 3, their sum should be equal to I'm leaving this open question. I'm not answering this over here. वन तो है ही ना, वन में क्या चीज है, वन में तो आप एन में आप 2 पुट करो, 2 स्टेप तो 30 आता है, तो लोअर एंगल 30 आ जाता है. 3 पुट नहीं, आप 2 भी पुट कर सकते हो, 2 पुट करो ना, इसमें क्या आता है, समझ नहीं आएगा. नहीं नहीं नहीं, वो इसके ये 22.5 है, आखिरी वाला एंगल 90 है, इनके बीच में आपने देखना है, टोटल 90. Just get me off this.